Hello. Hi, everyone. Welcome to the Temporal Graph reading group today. Um, for this week, we are glad to host Kiarash Shamsi, um, who will be presenting their recent work and also, disclaimer, I'm one of the author as well, called GraphPulse, Topological Representations for Temporal Graph Property Prediction in iClear 2024. And some more background about Kiarash. So Kiarash is a PhD student at the University of Manitoba, under the supervision of Dr. Junit um, Akora, who is also with us today. And he has published as a first author in conferences such as NeurIPS, iClear, and ICBC. And his research interests are temporal graph learning, GNNs, topological data analysis, and blockchain data analysis and systems. So I will hand the mic to you, Kiarash.
Thank you, and it was complete introduction. So I never had this much complete introduction. So thank you. Let's get started. So thank you everyone for having me here. So I'm Kiarash Shamsi from University of Manitoba, and today I want to present, this is our latest research, GraphPulse. It's a topological representation for temporal graph property prediction, and it has been accepted in iClear 2024, and we will be there for presentation in Vienna. So this work is a collaboration work between University of Manitoba, McGill University, Mila, University of Texas at Dallas, and also UCF. So let's get started. So before that, can you see my screen all? Is it okay? So
yes, we can see your screen.
Yeah, perfect. Yeah. So as you know, like today, in lots of different area of research, like financial tokens, geographical token networks, or flight networks, or traffic networks, or even structural networks like global internet, we are dealing with graphs. So right now in research area, graphs are everywhere. And the thing is, even though we have static graphs in many different area of research, real life graphs are a little bit different. So real life graphs are temporal, and time plays a really crucial role in temporal graphs. So we have timestamps, we have time sequences, and these are all an inevitable part of real life graphs. So in data analysis or graph analysis over these real graphs and dynamic graphs, we have two different settings to look at this whole graph space. So one way to deal with this timestamps graph is to look at these graphs in different snapshots. And we split the whole space of graphs to different time intervals, and these intervals can be daily, hourly, weekly, or monthly. So basically, we have a number of graphs, and these number of graphs are from T0, which is our base time, to it can be even to right now, or we can have some generated graphs also for the future or based on our setting. And we call it discrete time dynamic graph, which is really popular in temporal graph learning. And the next domain is continuous time dynamic graphs. And in this domain, we're dealing with graphs in a real-time stream of edges and nodes. So we are looking at graph and by coming nodes and edges to our system. So we are monitoring the whole network space, and we catch the new nodes and new edges as soon as they appear in the network. So this is the CTDG, the continuous time dynamic graph, and the second temporal setting. And whatever you choose for looking at your graph, so you can, at the end of the day, you can define like different learning tasks, and node classification, edge classification, so the traditional one that people tend to use this. We have also link predictions, which is really important in some domains like transactional networks also. graph classification, and recently in this work, we also proposed a new learning task in temporal graphs, which we call it graph property prediction. So, and what we mean by graph property prediction, that will be our main focus of this paper. So this is simple. So you have like your whole graph, time stamped graph from past to the future, and you split this to observation and prediction period. So you look at past, and you want to catch the behavior of the graph. You want to learn like the evolution of the graph in your observation period, and try to predict some properties for your graph in the future. So you have this continuous evolving graphs in your real world. So you look at these graphs in your observation period, and you predict the growth or shrinks in number of nodes, like in future. Or you can predict the density of the node. And these different properties, they have really crucial meanings in real world domains. So let's look at some examples here. So what we mean by property in finance domain. So in financial domains, predicting number of nodes and edges of future graphs, it has really significant meaning. It gives you some idea how this network will be behavior, or will this network successful in future or not? Is it good to invest money on this network or not? So these are all the questions that you can find the answer if you have like a good property prediction model here. The next is social networks, is really important property prediction task. So you want to predict the change of interactions and also participant in the network. So it can be interpreted to number of nodes and number of edges again in social network. And it is really important for also infrastructure problems. So you can have like plans for how do you want to allocate the resources to these social networks. And these are all problems that you can solve if you have like a prediction of number of nodes and number of edges in near future. And also in traffic networks, like geographical networks. So you want to predict like a traffic trend for tomorrow, or a traffic disruption, by predicting again number of nodes and edges. And number of nodes and edges can be interpret and translate to different applications in this domain. So this is what we mean by graph property. And what we do here in this project. So the main graph property that we focus on is network grows or shrinks in terms of number of edges. So number of edges in transactional domain, which is our main focus, is the number of transactions. So we basically want to predict if this network gonna grow or shrink in near future. So if you can predict it can grow in future, so you can invest some money on that, and this is a good thing. And if you see like a shrink, it's gonna happen soon. So this network is not promising for investment some money on that. So this is the main task that we want to do. And here is our problem setting. So you're looking at some data snapshots, and these data snapshots are weekly. And then you put a gap between that. So we put a gap because in transactional networks and in some social networks, the behavior of the network exactly like the next day after the snapshots is pretty similar to the behavior of the data snapshot. So the task will be trivial to learn. So it's not, we want to make our model even more challenging. To be challenged. So we put a gap, and we want to predict the next week behavior after 3 days. So we are looking at 7 days. Then we put a gap, and we want to predict like the next week after 3 days in terms of growth and shrink. And if we see a growth in the terms of number of nodes, the label is 1. If it's a shrink and we see a decrease in the number of edges, so it will be 0. So the problem is a binary classification. But here in this image, this is the label behavior of DGD token network. And for some of you that may not know, so we have different millions of token networks on Ethereum. So you can even have your own token network. People can come trade with your token. So this is one of that token. So this is DGD. It's somehow one of the popular one. So, and if you look at how this network behavior from 2016 to 2018, so there is not that much clear behavior. So sometimes you see some fortune in this network, people come and invest and do transactions, and then they get out of the network, so they come back. So this is like the trend of transactions in DGD network. So we want to basically predict this by
just
looking.
to clarify, for the label generation, you are generating, basically you're taking the data snapshots and computing the average number of nodes from that, and then the labeling window,
Edges.
you have the number of nodes or like the edges, and then you are comparing that average with the average from the labeling window, the green window that you are do, and then you decide if it's 1 or 0.
It's not average, it's sum, but yes, that's the whole setting is exactly.
So does this mean you predict one number for the full labeling window? So for all 7 it's okay.
It's a binary label. So it's the meaning of these labels is, so do we have like a decrease or increase in in terms of the number of transactions in the next snapshots. So this is the whole setting. So we want to capture like this behavior. So the whole idea here that we are revolving around. So how can we learn this behavior and try and predict this property prediction in future? So we want to define a phase space here, and we want to define a trajectory in phase space. So this is how we deal with this problem. Our setting this trajectory in phase space, we inspired that from Newton's law of motion. And what we mean by a phase space refer to a multi-dimensional space where we want to map the state of the system by some set of coordinates. And basically, if we want to make it easier, we want to map like each snapshot or each graph to a space, and we want to learn some coordinates and some variables out of that, and then we can capture the behavior of the network. So a little bit more about what we mean by phase space. So in our phase space, just assume that we have a space that you can map each graph or each snapshot to that. So in this space, each graph instance represent a pointer, and you can have some corresponding coordinates and variables of that. And in this network, graphs like daily snapshots, weekly snapshot, they have their own representation, and you can see the evolution of the graph. So it can be visualized, and we can see the path of this trajectory or the momentum of the network through this through the time. And what we want to do with this phase space, we want to learn the dynamic behavior of the graph here, and we want to extract some features from this phase space, and then we want to use these features for predicting the property of the graph in the future. So this is the whole idea here. So to make it a little bit more clear, this is a good example that we create. Also, it's available in our paper. So this is a sample phase space. We create a tiny one, like a small one. So this is a power law phase space. If you know like the power law in token networks, if you define it on node degree, it can show you that if you have like a centralized node or you have like a distributed transaction network. What I mean by distributed, so in transactional networks, sometimes you have some nodes that they have lots of transactions, so they are somehow controlling control over the network. So these are exchanges, a community, so they are leading the networks, and other people are ordinary people like me, you, and we go there and like buy networks, trade networks. So if this factor of alpha, like the power law, goes up, it means that you have more, you have some central nodes. The distribution is low, so you have, let's say, small number of these central nodes. Most of them are central, and the number of other people like trading is lower. So your network is more central. So we define this sample, two-dimension phase space just to show what we mean by a trajectory here. So if you look at this network, this is 8x network. So we have some daily snapshots, daily graphs, and we get the alpha factor of that and also the number of nodes, and we just map each graph to this phase space. So if you look at these points, for example, this is the graph for this date in 2017. And here we have about 600 nodes, and alpha was something around 6. So, and this path, like this evolution path, is what we want to learn here. So what we're trying to capture is this evolution path. So this is a sample what we mean by phase space. And now it's time to talk a little bit more about topological data analysis, because this is our candidate for the phase space in next system. So I think maybe lots of you know about TDA, but TDA is a tool that can learn topological feature from your data. So it can look at your data in topological way, and it can extract some structural shape of your unstructured data. So you have some like a graph, and you don't have any idea of the structure of the graph, but Topologic lets you extract some structural features from this unstructured graph. And this is really good for noisy and high dimensional data sets, and I will show you shortly what I mean by that. So how it can help us with noisy and high dimensional data sets. And by the way, TDA is a kind of umbrella, so we have lots of different things here. So here in this project, we use the TDA mapper tools. This is one of TDA methods and tools. So our assumption, that we make our idea around that is TDA can capture this trajectory. So if we use TDA here, we can have some good insights of evolution in graphs. And why we think so? Because if we use topological data analysis, we have some topological features, and these topological features can be extracted from the structure of the graphs. So, and behavior of the graphs, it really depends on the structure of the graph. So if you add nodes, if you add edges, so it can change the structure of the graph. So you can capture this by topology. You can look at the graphs and get these features. It has a robust representation. So before I start, talk about what I mean by robust representation, I need you to look at these two images. So a really good insight here. This is a daily transaction graph of an Ethereum token, and this is not a big one. So this is really a small transaction network of just 1 day of a transaction token. And if you look at this, it's super sparse. So you have lots of nodes, and they are just coming to the network. They trade, like buy, let's say some, I would say Bitcoin, because you may know Bitcoin, but it's not Bitcoin super big. But let's say it buy some tokens and you go, you don't do any other transaction. You just save it on your wallet. This is the only transaction that you do. And this is these nodes here. And if you look at here, you have two central nodes. So these central nodes are communities, center, or these are like exchanges. So you buy tokens from these guys. So because of that, all of these people transacting with these central nodes. So in this super sparse graph, we really don't care about like adding one node here. So like adding one people here and just transacting to the network, it doesn't change the representation of the graph. So we have two central nodes here, and we have some people here transacting. It doesn't matter 2, 10, or 20. In somehow it may matter, but like 11 and 12, we don't care about that. Just one people or two people. So if you want to look at this the original graph, so you basically have all of these nodes, and it's really messy. So it's really hard to deal with all of this sparsity and these noises, and people are coming, people are going. So GNN, if you apply GNN on that, so it's really hard. But what we do, what TDA do, TDA convert this really ugly sparse graph to this beautiful one. That side, it's really clean. So if you look at it, this is real world example. So it's not just like a fancy one I created for the screenshot. It's really a real world example. So we created this graph to this one, and in this graph, each of these nodes is a cluster of these nodes. So you can see some structure here, and what I mean by robust representation, so this graph is robust to noises. So if you just add some random node here, this whole representation not going to change that much because these nodes goes to, the relevant cluster. And so you have like a clean graph, and as soon as there is some fundamental change or important change in this network, so you can have different representation or added node or edges here. And this is really cool. And also we have multi-resolution here. So you have two different things to look at. So you have the original graph, you have also the TDA graph. So you can look at your phase space, basically your snapshots in two different angles. This is really important. So you have lots of information to look at for capturing this evolving behavior. So now it's time to a little bit talk more about what we mean by TDA mapper, how this gonna work and how we use that. First of all, it's important to know TDA mapper has been designed to work with point clouds. So the first thing that you know is this whole setting, the TDA mapper is working with point clouds. So we are dealing with graphs here. So what we want to do, we want to go from this graph, the sparse, hard to look at, and really we don't know like the evolution, to this clean one, and we want to monitor the evolution on this graph. So going from this to this using the TDA, we need to first convert this graph to a point cloud that TDA can deal with. So the first step in using TDA mapper in all of the networks that, or whatever you want to use, is converting your things to a point cloud. So first thing that we do, we use a structural encoding. I will explain like how we do this in structural encoding in my next slide. So we create a point cloud out of these graphs, and in this point cloud is created based on the positions and the structure and topology of this network. So next thing in TDA, so I'm just explaining it's really easy because I want you all to understand so what we are exactly doing. So we create some covers. Let's say we create some cubes here. Not covers. So we create some cubes here, and we put these cubes on this point cloud. So what is this cube? So this is arbitrary number of cubes and also overlap. So we define these two, and we put some cubes on this point cloud. So just like tiles, and then we map this space to a 1 dimension, 2 dimension, or whatever based on a cover function. So this cover function brings all of these points to a lower dimension. So here is just a simple height function. So here these nodes have higher heights, so they map to higher place here, and these are mapped here. So and based on the overlap of these tiles here, you create some edges between these things. And inside each tiles, you also do a cluster. So you have this tile, all of these nodes will go here in this cluster. So this node is basically contains all of these nodes. And what are these nodes? These nodes come from here. And also, how you put edges in this graph, you put edges if you have some overlap between these tiles. So if you have, for example, here you have an overlap between the blue one and the green one, so you put an edge here. And you do also a clustering inside each tile. So by doing this, you convert this graph to this one. And in this graph, each node is a cluster of same behavior nodes, and also each edge connect two different clusters. How? If they have some overlaps here, if they have same nodes that we can find in both clusters. So in this way, we can also connect the clusters. So this is the whole idea how TDA mapper works in a very simple way. And what we do next, so we do this TDA mapper to create a phase space. And what is our phase space, this is a TDA mapper phase space. So in this phase space, each point is not an original graph. So if you remember here, so each point was the original graph, but here each point is the TDA representation of that graph. So you have a space, basically in this space, each point represent the TDA, transformation of that original graph. And let's look at an easy toy example that we created. So let's say here the mapper length is the number of neighbors. So what you do, you create a TDA graph out of this. So here you have 3 nodes with just 1 neighbor, and all of these 3 goes here. So you have cluster of 3 nodes. And also you have this central node, and it has 3 different neighbors. It goes here in this little one. And you create this graph. This is TDA representation of this. So you go to next day. This is tomorrow. So we have 2 more people trying to buy some coins from this exchange. The whole behavior not changed that much. We again have a central exchange and some people trading with that. So this is what we want to know from this network. We don't really care. 3 people are buying token from this central node or 5 people buying from this central node. So what TDA do again? TDA create exactly same structure here. Again, we have a cluster of 5 nodes that they have 1 neighbors, and we have also 1 central node that these people are interacting with that. But what happened in third day? So in third day, we have an interesting triangle here. So these people are not just buying a token from the central node. These people are trading some token here. So what we see here, we see a boom. We have another structure. So we could capture that. So this is what TDA phase space can do. So here we have 4 nodes. Here, these 4 nodes, they have 2 neighbors. They come here, and we have 1 central node again here, and 1 ordinary people just buying token here. That's interesting. So what the hypothesis here is trajectories can be captured efficiently by using TDA mapper. And we need to do an empirical evaluation to show that. And what we do here, we use 2 well-known graph generator, Erdős-Rényi and also Barwasi-Albert graph generators to prove our TDA idea more empirically. So before going to the setting of this empirical design, so let's create a tiny settings here. So we want to show that TDA graphs can capture trajectory better than raw graphs. So if you remember, we have a multi-resolution space. So we have the original graph from this side. We have the TDA graph from this side. We want to say that if we use TDA graph, we can better capture this trajectory. And to showing that, so we create a sample space. So this is what we create. So we create a reference graph. So with both Barwasi, Albert, and Erdős-Rényi. So the setting is pretty same. We have a reference graph, and then we create some neighborhood around this graph. So different layers means different neighborhoods. And we put 2 criteria, 2 simple criteria to these networks. So first criteria is all of these first up neighborhoods should be more similar to this reference graph than the next up. So this is trivial. So when you go, farther and farther from here to so far, so these nodes here should have more, greater dissimilarity, not similarity, dissimilarity to this reference network. So this is one assumption that we have here. So this is one criteria. And the next criteria that we put here is the first hop neighbors should be similar. So you shouldn't have like a very, dissimilar graph here. So these are all pretty same. So we create this setting, and the first hop neighborhood is, it contains 8 different graphs. And what we do here, we go through this setting to somehow show TDA's strength. What we do, we create TDA representation for all of these graphs. So you have this space, we extract node features. Node feature here is positional encoding. And we create TDA maps. So this positional encoding is converting these things to the point cloud that I explained before. And then we create the TDA mapper on top of that, and we have this space. So all of these graphs are TDA mapper graphs, representation of this original graph. And then what we do, we compare this reference graph to the one time with this graph, we get the similarity, and one time with the TDA representation. So we know that these are all similar. We don't have a really significant change in similarity score. But we want to see how this behavior. So this, if you look at this, we again have this star shape. We don't know. We know that behavior is pretty same. So we don't want to see a big change here. And also these are two representation of that. So TDA representation are pretty same because they both are star-shaped graphs. So, and the results are interesting. So this is the dissimilarity score of original graphs in Erdős-Rényi. And if you look at that, you have some sharp decrease, increase, some fluctuation here. And this is TDA. TDA is pretty smooth because we don't see any like big change or anything here. So the behavior is very, fixed. So we have like somehow a straight line, and this is what we want to see. So we show that TDA can deal with noise and it can capture the behavior. So if you see a different representation, this can be go out. And based on this idea, so now we showed that TDA is really a powerful tool for capturing this behavior and creating your phase space. So we create our framework, GraphPulse, around this idea to predict the graph property, which was our initial task here. So in GraphPulse, the steps are like that. So we have the whole transaction network from, let's say, this is for 1 year, 2 year, it can be whatever. And then we want to fit it to our discrete setting. So we first extract the snapshots out of that, doing a discretization. And then we have 7 days of snapshot. So here our intervals are weekly, because weekly is a good snapshot period for financial dummies, and our focus here was financial dummies. So 7 days is good. So if we can predict for next week. And then you have daily graphs. So you have like a snapshot of 7 days. Then for each day you have a graph. This is your original resolution number 1. So your original graphs. Then you transfer each of these graphs, create a point cloud out of that, and then create a TDA representation for each graph, each daily graph. Then you have your second resolution from this. So you extract some features, TDA-based topological features from the first one that shows the behavior change. And from this side also you have some raw features. This is from your raw graph. So you can have also some features from this original domain. Then you use both of these powerful features, and we use RNN, LSTM GRU model. It's a hybrid model. We put LSTM and GRU both to learn our both long-term and short-term. And then we predict our label, which is our graph property here in one of our settings, the growth or shrink in number of edges, the number of transactions. A little bit dig deeper in this network in terms of model parameters and model details. This is a structural encoding that we use for creating the point cloud representation out of our graphs. So we use these 4 features, edge weights, incoming, outgoing, so because these are all directed graphs, and our length is a 2D TSNE dimensionality reduction. So we have this point cloud, we map it to a 2D space, TSNE, and then we put our cubes there and we create this network. From other side, we have original graphs. Then we get these topological features. So number of nodes, which are number of clusters here. So nodes are different here. So nodes here are clusters. Number of edges, which means different cluster interaction. Have maximum cluster size, which shows you like the maximum similar behavior here. So all of these people, like ordinary people, will go like to a cluster, and you can get the maximum number of these people, for example. So average cluster size and average value of edge weights. So these are the things that you have. And from other side, you have number of nodes, number of edges, and average value of edge weights. And you pass both of these things to RNN, and we train how to predict the property. So let's take a look at some experiments that we do. First, a brief description of datasets. So this part is my interesting part. So we have some real world datasets here. So we have transactional networks from Ethereum. In this project, we use two different domains. We use social networks like Mass Overflow and Reddit Body. These are a really common one. People use these datasets everywhere, but these 7 networks is part of our contribution here. We have these datasets. These are real world transaction network that we extracted from ERC20 token networks. And these are all timestamps. And we do our experiments on these 7 ones, and these are some of them are some famous ones, like for example Bank or ADEX. And here I want to also tell you, so we have Chartalist. Chartalist is a repository for ML-ready datasets. So this is one of our other papers. So I also present this before in Temporal Graph Group. So if you need temporal real-world token networks, you can use Chartalist. We have different tasks there. You can work with UTXO account base. So we have Bitcoin data there. We have also Ethereum data. Different tasks has been defined there. So if you want, all of our datasets are publicly available there. You can use them. And also we have some tools for you for data loading if you want to try to use real world token networks in your project. So feel free to use our Chartalist project. So let's get back to experiments. So here in experiments, we define some state-of-the-art model to compare our setting with that. So here we use Evolve GCN, GRU GCN, and HTGN. And as you know, these models are all recent state-of-the-art temporal graph learning models. So basically, these models has been trained and optimized for node level tasks, but we did a minor change. We add a pooling layer, and now they can do property prediction as well. Also, from the other side, we also use some base models. So we use GIN, and we train this GIN for graph property prediction on the first resolution, like the original graphs from one side. And then we train this GIN on TDA graphs from the other side. And we compare this base model to all of the other models. And you can see like GraphPulse yields the SODA models significantly, because it shows that TDA phase space can really work here. It can capture like this behavior. And this graph neural networks, it's hard really to deal with these real world transaction networks because of the sparsity and the change of behavior that I told you. So this is results for network gross property prediction. Also, we tried two different other properties. So we try to do a node count property prediction. So this is basically how many new nodes added to your system. So this is investors or communities that are coming or going in a network. Again, GraphPulse could do a very good overall performance over others. So, and also we put a more challenging task. So let's go to a little bit more challenge. The density prediction is really hard because in these networks, it's a really hard task. So we did this task also, and again, GraphPulse could have like some good results. And we could also here build some SODA models, and the overall performance was good in this even challenging task. And a little bit about time experiments also. So this part is also worth to look at. GraphPulse use TDA mapper to extract the phase space. So it has like TDA extraction. It has also the RNN to be trained. So we compared different models that we are using here, and this is the whole time that we have like end to end. And GraphPulse could have better results, like 26% faster than HTGN, which is I would say the state of the art, one of the most important state of the art model here in this network. And it had good results as well. And also you may ask, what is TDA cost also? Because like TDA cost, this is also an important part of this network. You need to do lots of things there. So TDA cost, we create a cost experiment here. So we extract different TDA feature graph like using Erdős-Rényi, and we have different number of nodes here. So this is basically the time of extracting the TDA mapper representation out of that. So and with something around 40,000 nodes, so the time can surpass about 1,000 seconds. So the time is good. It can be scalable. It can be even optimized for large networks. And one more thing that it's worth to mention here is TDA parameters. So if you remember, when I was talking about TDA, I told you that in TDA we have two important things to do after you create your point cloud. So first thing is choosing some cubes to put on your data, and then choosing the percentage of overlap of these cubes. So you have, let's say, a point cloud in space, in whatever dimension you have, and then you want to put some tiles on that. So the number of these tiles that you want to create is one thing that you need to choose if you want to have a good TDA representation. And the next thing that you need to look at is the percentage of overlap that you consider, I mean, for each cube, like how much do you want these cubes to have overlap with each other? So if you put, for example, 100% or 1, so you have different cubes, and these cubes are all overlap. So basically you have just one cluster, and everything in your graphs goes to that cluster, because you have like one big cube, and the overlap, you have different cubes, but the overlap percentage is 100%. So all these cubes can look at the whole, point cloud. So you have basically just one cluster. So this is really important how you choose these two numbers. So what we did here to show how we choose these numbers, so we did a grid search here based on different number of cubes and percentage of overlap, and we could show that we have a zone, we have a region here, and this region for token networks are pretty close. So because the behavior of these networks are pretty close, so you can deal with this network in the same way as well. And if you choose your parameters from this region, so you can have really good representation for TDA graphs, and this can be really interesting. So this was one of the challenges for this network, and this is the way that we deal with. And yeah, that was GraphPulse. And the way that we use and we leverage topological data analysis to do a graph property prediction in temporal setting. And thank you for having me here. And if you have a question or do you want to discuss, so let's discuss. And it would be great if we can talk more. This is my email, so we can work together, or we can talk about like how we can use TDA more in this area. And also we have GraphPulse deployed on our GitHub. So if you want to take a look at our code or use this framework for doing graph property prediction, it's there on our GitHub. Thank you.
Yeah, thanks for the nice presentation, Kiarash. Yeah, so if you have any question from the audience, feel free to type in the chat, or unmute yourself to ask the question. Yeah, so I think it's interesting that different properties, the models have different results as well, right? Like it's like expected, but also they can change quite a bit. So I think because this is one of the first work, well, this is the first work that does temporal graph property prediction. There's a lot of things that we don't understand as well, right? So I think the task itself is also one of the main contributions of the paper, which is super interesting, and also it's like it's quite unique to temporal graph because we have this evolution of graph structure, and basically predicting how the graph will look like in the future is something that's also very important for many downstream tasks. So if anyone is interested to work on this like this problem as well, like I think this could be like very interesting as well, and to try different approaches.
Exactly. I just want to mention that we have lots of space to do research here. So this is basically the beginning of the way, not the end. So, and we are open to chat with who wants to work in this area. So because it's pretty new, so feel free to email us. We can go for the next step that we can take in property prediction, which is pretty new in temporal setting.
Yeah, and also like in general, graph level tasks are significantly less studied in temporal graph than link and node level. So I think it's interesting to think about what kind of architecture would work better for graph level and can better summarize the graph. And then it doesn't have to be the same like architecture for link and node. Like for example, on static graphs, the graph transformers are one of the most powerful like techniques for graph classification tasks, but that's not necessarily the case for link prediction and node classification, for example, because the required information is more local, like in these more like local tasks. So there's a lot of like interesting direction to take. So if there's no question from the audience, so then let's thank our speaker again. Yeah, thanks for the presentation, Kiarash. And yes, see you all next week at the reading group.